And the three nodes are identified: I at 0 and -1, J at 2 and 0, and M at 0 and 1. So this is node 1, node 2, and node 3. We are given E to be 30 times 10 to the power 6, nu to be 0.25, and thickness of 1 inch. We are asked to find the stiffness matrix for the element and sigma if U1 is a 0, V1 is 0.0025 inches, U2 is 0.0012 inches, V2 is a 0, and U3 is a 0, but V3 is 0.0025. Oh, sure. Is that better?
Yes, thank you.
After we find sigma, we also want to find the principal stresses and the principal angle. Right. And the very last thing we did on Tuesday, we were able to express K as equal to T times A multiplied by B transpose times D times B. And we learned that B is equal to BI, BJ, and BM, where BI is equal to 1 over 2A times beta I, 0, 0, gamma I, and beta I. So clearly, in order to get B, we want to solve for beta I, gamma I, and of course, to get BJ, we're going to need beta J and gamma J, and to get BM, we're going to need beta M and gamma M. So if I start with these, we've already identified beta I as equal to yi minus ym. And these are based on the coordinates of the nodes, where I is the first node. So I will go here, yi minus ym Hmm? Going back to the notes. Hmm? Is y? Yj minus ym, right? Yes. Okay. So yj minus ym. So if I look here at the yj, I'm looking at a 0 minus ym, I'm looking at 1. This is equal to minus 1. Gamma I is xm minus xj. So xm is a 0 minus xj is a 2. I'm looking at a minus 2. Beta j is equal to ym minus yi, and ym is a 1 minus yi is a minus 1. So I get here a 2. Gamma j is equal to xi minus xm. So I get a 0 minus a 0, which is a 0. And then beta m is a yi minus yj. Which is a minus 1 minus 0. So I get a minus 1. And gamma m is xj minus xi, where xj is a 2 minus xi is a 0. So I get a 2. So now I can write B, but we also need to evaluate 2a, right? And if you recall, 2a is equal to the determinant of the matrix X, where X is equal to 1 xi yi, 1 xj yj, 1 xm ym. So this is equal to 1, 0, minus 1, 1, 2, and 0, and m here. So I got 1, 0, and 1. (2a) is equal to the determinant of the matrix X. So this is equal to the determinant of 1, 0, minus 1, 1, 2, 0, 1, 0, 1. And we can find that to be equal to 4. Oh, yeah. So Is this still good? Okay. And as I mentioned that, it is worth noting that the inverse of x is equal to 1 over 2a multiplied by alpha I, alpha j, alpha m, beta I, beta j, beta m, gamma I, gamma j, and gamma m. And we have already identified 2a and all the alphas, betas, and gamma. So now if I use the alphas and betas and gammas we identify here, I can write the matrix B, can write the matrix B, right? So we can come here and say B then is equal to, and first we have 1 over 2a, 1 over 2a. So I have 1 divided by 2 times 2 is a 4. Okay. And then I'm going to have beta, I'm sorry, bi, which is beta I 0, 0, gamma I. So beta I is a -1. Then I have a 0. Then I have a 0 and a gamma I, which is a -2. Then I have a gamma I, which is a -2, and a beta I, which is a -1. And we're going to repeat for the J's and the M's. So I have here for the J, I'm going to have a 2 and a 0 and a 0 and a 0. And then I have gamma J, which is a 0, and beta J, which is a 2. Okay. Then we're going to go to beta M and a 0, 0 and gamma M, which is 2. Then I have a gamma M and a beta M. So this is my B matrix. Since it's a case of plane stress, we have the relationship that relates the stress to the strain via D, where D for plane stress is equal to E divided by 1 minus nu squared multiplied by 1 nu 0, nu 1, 0, 0, 0, and 1 minus nu over 2. So if I evaluate D, I will get 30 times 10 to the power 6 divided by 1 minus, and nu was given as 0.25 squared multiplied by 1, 0.25, 0, 0.25, 1, 0, 0, 0, and here I have 1 minus 0.25 divided by 2. So here I have my B and I have my D, and the thickness is given, and we found 2A, so we can also, of course, A would be equal to 2. The thickness is given as 1. I can solve for K equal to T times A times B transpose times D times B. Now this can be easily done using matrix manipulation on a computer, right? So we can find K, since I have B, I have D, and I have T and A. If you do the math, you're going to find K to be equal to 4 times 10 to the power 6, multiplied by, and remember, K is a 6 by 6.
Can you just quickly go back to where, like, a little bit down? Isn't it TA, B to the T? The K.
B transpose. Sorry. Good. Any questions? So when I do the math here for a 6 by 6, I will get a 2.5, a 1.25, a minus 2, a 1.5, a minus 0.5, and a 0.25. These corresponds to degrees of freedom, UI, VI, UJ, VJ, UM, and VM. And for the columns also UI, VI, UJ, VJ, UM, and VM. Yes, this is a symmetric matrix. So I'm going to put here my diagonal that is always positive. And minus 1.25, and this is symmetrical. So this is the first thing that we were asked to find, is the stiffness matrix for that triangular element. And as I'm mentioning that here, of course, we can find an expression for K, a lengthy expression for K. And there is one section in your textbook where they evaluate K. But many times, if you're using like MATLAB or Excel, once you find, if I define B, D, T, and A, it is easier just to find K numerically. So next.
I was going to ask about the orientation of the element. So would this be considered like a negative 90-degree rotation?
Okay. The key here, the question is about the orientation of the element. So looking at this element, of course, I don't really have a structure, so I don't have a local and global coordinates. But should you be looking at a structure, most likely or typically, we pick the horizontal and the vertical as the global axis. As long as the element axes are parallel to the global X and Y, then there is no transformation. So even if these were the local axis for the elements, the X, if this was the X prime, it is parallel to X. And if this was Y prime, it is parallel to Y, and I do not need to apply transformation. Very good question. So next, we want to evaluate the stress. So the stress sigma, which is a 3/1, may be evaluated using D times B times D. So I can evaluate the stress using the nodal displacements. So D is a 3x3, and B is a 3x6, and D is a 6x1. So you can see here, this is balanced. We are given the displacements. So the displacements are given in the statement of the problem. We just evaluated D and B. So the only thing that is missing here is to put D, and I can write D using the displacements that are given. So I have U1 is a 0, V1 is a 0.0025, U2, which corresponds to J, by the way, is a 0.0012, V2 is a 0, U3 is a 0, and V3 is a 0.0025. So this is D. So when I do the math, I'll find that sigma, which by the way is going to give me sigma x, sigma y, and tau xy. This is equal to 19,200, 4,800, and a minus 15,000. These are in PSI. Just to remind you, state of a plane stress using a stress element. If this is my x direction and this is my y direction, then this would be my sigma x. This is my sigma y. Similarly, sigma x and sigma y, right? And my tau xy, and I'm showing them all in the positive directions. So this represents a state of a stress at a point. But we are also asked to find the principal stresses and the principal angle theta p. So in order to find the principal stresses, can use the principal stress equations we learned in solid mechanics. So I can find sigma 1 is equal to sigma x plus sigma y over 2, and I'm going to write 1, 2 here, plus or minus the square root of sigma x minus sigma y over 2 squared plus tau xy squared. If I plug the numbers, I'll find that sigma 1 is equal to 26,639 psi. Sigma 2 is equal to minus 4,639 psi. These are also known as major principal stress and minor principal stress. To find theta p is equal to 1/2 tan 2 tau xy divided by sigma x minus sigma y. So theta p. Question?
Yes, I saw. Is this 1, 2? I saw.
Oh,
Yeah.
you said it's stress 1, 2, 1 and 2.
Okay.
Yeah, plus and minus. So one, the plus is for the 1 and the minus is for the 2.
Okay.
Actually, on
Excuse me?
10.
Yes, yes. Thank you. Okay,
And can you just move a little bit to the?
sure.
Thank you.
So theta p, this would be like 1/2 inverse tan of 2 tau xy. We found it to be minus 15,000 divided by sigma x, which is 19,200 minus sigma y. And we found sigma y to be 4,800. So theta p is equal to minus 32.2 degrees. So what does that mean? If I'm looking at my stress element, the principal stresses are going to be acting at an angle. So this is going to be my principal direction 1. And this here is the angle theta p. And we are going in the clockwise direction. So we can, this is why this theta p is minus 32.20 degrees. And perpendicular to that in the orthogonal direction, we're going to have the 2 direction.